Okay, Jai Hind. We start with the Fourier transform. That is the topic of unit 3rd. And before going to discuss with the Fourier transform, we are here to just understand what is the waveform symmetry that is used in the Fourier transform. Then here it is. Okay. So if the periodic signal ft has some symmetry, then sum of the trigonometric Fourier series coefficient may become 0 and calculation of the coefficient becomes simple. The purpose of to study the waveform symmetry is that we reduce our calculation. Okay, basically if we know that our waveform is symmetrical, then sum of the coefficient that becomes 0, and that is very easy to perform the further calculation. So there are following type of symmetry. First one is even or mirror symmetry. Even means like this one. If even function, they are symmetrical about the y-axis, we can say that, like cos function. So these type of periodic function that are even symmetry, that have a even symmetry, the signal which are symmetrical about y-axis, vertical axis, that are called the even or mirror symmetry. Number second, that is odd or rotation symmetry. Odd means the function that are symmetrical about origin, like sine function. This is odd. So they are symmetrical about origin. So these two are very main symmetry that we have to observe in any waveform. The third one is, that is half wave symmetry, we'll discuss, and the last one, that is least important, quarter wave symmetry. So here three are most important. So we going through the derivational. Here the signal ft is said to have even symmetry if the function is ft equal to f of minus t, and here you can see that the same value are here, 0, pi, minus pi. If we are replacing t by minus t, then we will get the same value, means ft that is equal to f of minus t, f of t equal to f of minus t. We change the sign of t, that is time, but we will get the same value. The value of function would be same. It doesn't depend on the direction of the time, where it is positive or negative. Okay, so that is called the even symmetry. And this, in this waveform, the Fourier series coefficient bn, that becomes 0, and a0 and an are to be evaluated. Okay, bn 0, then we are having only 2 left to calculate. Okay, the sum or product of 2 or more even function is an even function, and with the addition of a constant, even nature of the function is still preserved. These type of function are always symmetrical with respect to the vertical axis, as discussed earlier. So here you can say that this type of waveforms, square, triangular, okay, so these type of waveforms, if it is given in question, then we already know that it is it having the even symmetry, and it means that the bn, that is the Fourier series coefficient bn, that becomes 0. We need to calculate only two coefficients, that is a0 and an. So how we calculate the value of a0 and an, that also become easier. Okay, so if a function ft, that is the summation of f0 t and fet. f0 t means odd function, and ft, that is even function. Every function is summation of two functions, odd and even. Okay, in ft is even function, then f0 t, that becomes 0. Okay, and ft becomes fet. Then the a0 is equal to, as per the formula 1 upon t. Here it is minus t upon 2 minus t upon 2 plus t. T is the time period of that particular function ft dt, and here it is 1 upon t minus t by 2 fe, because ft is even signal, and here a naught becomes this one, that is 2 times of, because it's even symmetry, because we are having like this one, it is minus t by 2, it is t by 2. So we can calculate it, the area of this waveform over 0 to t by 2, and the total is 2 times of this 0 to t by 2. That's why the a naught becomes 2 by t, 0 se t by 2 fe t dt, because of the symmetry. Now the a naught have become this one, okay. And what about the an? That also becomes 2 upon t minus t by 2 se t by 2, and here we reduce it, minus t by 2 to t by 2, that becomes 2 times of 0 to t by 2, and here it becomes 2 into 2, that becomes 4 upon t. So that's why an, that is 4 by 2, 0 to t by 2 fet cos n omega t dt, and we already know that the bn becomes 0, okay, because ft sin omega t is an odd function, and we already know that if you are integrating an odd function with a time period, that becomes 0, okay. So here the summary is, the coefficient a naught may or may not be 0, coefficient an is given by this one, and bm, that is equal to 0. Okay, odd rotational symmetry. So that is the opposition of even signal, means ft is equal to minus half f minus t. If you are replacing the t by minus t, then the value of function get reversed, okay. So that is called the odd symmetry, the function have a odd symmetry, and in this case the value of a naught and an both becomes 0, the value of a naught and an both become 0. Only we have to evaluate the value of bn, okay. So sum of 2 or more odd functions is always odd, and if a constant is added, the odd nature of the function is removed. So these type of functions are always anti-symmetrical with respect to the vertical axis, and the product of 2 odd function is even, as we already minus into minus, that becomes plus. And here these are the examples of the odd functions. These functions are the symmetrical about the origin, they are anti-symmetrical about the y-axis, okay. And here it is an 2 upon t minus t by 2 to capital T by 2 ft cos n omega t dt, and already here we see that this one is even function, and this one is a odd function. So odd into even, that becomes odd, and we already know that over a time period the integration of odd function, that becomes 0. That's why the value of an becomes 0, okay. As here it is written as f naught t into cos n omega t, that is an odd function, because of this one, odd into even, that becomes odd. And what about bn? Bn, this one is odd function, this one is odd function, odd into odd, that becomes even, okay. So integration of even function, that becomes 2 times of the half of the their integration period. So here we have double it, and integration limit, that is reduced to 0 to capital T by 2 f naught t sin n omega t dt, okay. Here it is half wave symmetry. A periodic signal ft is said to have a half wave symmetry if ft is equal to minus of ft plus minus capital T by 2, okay. And in this function, it is neither purely odd or nor purely even. So for such case, a naught becomes 0, only a naught, that is the DC value of that particular waveform, that becomes 0, and when n even, then an equal to 0 and bn equal to 0. When n odd, then an becomes this one, okay. changing the variable from t to t plus capital T by 2 in the second integral, we will get the value of a n is this one, 2 upon t 0 say 0 to t by 2 ft cos n omega plus 0 t by 2 ft plus capital T by 2 cos n omega t plus t by 2, as we have changed the integration from t to capital T by 2, and using the property ft that is equal to that we are already discussing, that is half wave symmetry minus f of t plus minus t by 2, we will get the value of a n that becomes 0 for n even, and it becomes 4 upon t 0 to t by 2 ft cos n omega t dt for n odd. Okay, these things all about the integration, nothing else. And here it is bn, that is the value of bn that becomes 0 for n even, and it becomes 4 upon t integration of 0 to capital T by 2 ft sin omega t for n odd. So these are the value of Fourier series coefficient for various symmetrical or n symmetrical system. Quarter wave symmetry, if ft is said to be have quarter wave symmetry if ft equal to f of minus t, or ft equal to minus half f minus t, also ft equal to minus f of t plus minus t by 2. Okay. So a function which have either even symmetry or odd symmetry along with the half wave symmetry is said to be quarter wave symmetry. Means that the function must have at least even or odd along with the half wave symmetry, that becomes the quarter wave symmetry. Okay. So here when we are considering it odd and half wave, in that case a naught becomes 0 and a n becomes 0, and here the value of bn that becomes 8 upon t 0 to t by 4 ft sin omega t dt when n is odd. Okay. And here it is ft equal to minus f of minus t, that is considering even and half wave. Then the value of a naught becomes 0 and bm also 0 when n is even, and the value of a n that becomes 8 upon t 0 to t by 4 ft cos n omega t dt. Okay. So this is the example obtain the trigonometric form of Fourier series for the sum shown in the figure. So here as we see that this is a odd function, this is odd function. Okay, because this waveform is symmetrical about the origin. Has odd symmetry, it means a naught and a n becomes 0. We knew that about the odd function, a naught and a n becomes 0. We only need to calculate that is the value of bn, that becomes 2 upon t minus pi to pi, or we can write it 4 upon t. 4 upon t, what is the value of t? That is the time period minus pi to pi, that is 2 pi. So 4 upon 2 pi 0 to pi xt sin n omega t dt, and bn becomes this one, and the value of function xt, that is a from 0 to pi, the value of xt is a. So here with the help of integration we have derived it, and it becomes minus 2a upon n pi cos n pi minus cos 0, cos n pi that is equal to the minus 1 ki power n, and cos 0 that becomes 1. So minus 1 to the power n, if n is even it becomes 0, because if n is even it becomes 1, 1 minus 1 that becomes 0, and the value of bn becomes 0, and for n odd it becomes, for n odd, so minus 1 to the power n that becomes minus 1, and minus 1 that becomes minus 2, minus 2 into minus 2 that becomes 4, it becomes 4a upon n pi, and the expression of xt, that is if you are putting the value of n 1, 2, 3, 4, 5, then it becomes 4a upon pi sin t and 4a upon 3 pi sin t, because for n equal to 2, the value of bn that becomes 0, because n is 2 is even, and so on. That is the expression of xt. Now we are going to discuss the Fourier transform. So what is the Fourier transform? Fourier transform is a transformation technique which transforms signal from continuous time domain to corresponding frequency domain and vice versa. means Fourier transform. We are having a signal that have a variation in the time domain, but we need to follow the system with the frequency domain, means we have to analyze the system, how the system is working with the frequency domain. Okay, then we can transform it using Fourier transformation. It applies to both periodic as well as aperiodic signal. That is the main important thing. So it can be applicable, as we see in case of Fourier series expression, that we are having only periodic, but here we can do with the periodic as well as aperiodic signal, non-periodic signal. Fourier transform can be developed by finding the Fourier series of a periodic function and then tending to t to infinity. The Fourier transform of a non-periodic signal xt is given by this one, minus infinity to infinity. Xt is the non-periodic function, xt is the non-periodic function, and multiply by e की power minus j omega t. Omega is the angular frequency. Angular frequency. You can write it 2 pi f in radian per second. Okay, so here, that's why we have here written x omega, because this xt is transformed into x omega, the variation of the function in frequency domain. Okay, the x omega represents the frequency spectrum of xt and is called the spectral density function. And similarly, xt can be recovered from its Fourier transform by using inverse Fourier transform. If we are having the function in the frequency domain, so we can change the domain of that particular function in time. Okay, so that is called the inverse Fourier transform, and we are having here the expression is that xt equal to 1 upon 2 pi minus infinity to infinity x omega e की power j omega d omega. You can see there is some similarities in the expression here, x omega e की power j omega t d omega. Here it is xt e की power minus j omega t dt. So these are the, this is for Fourier transform, this is for inverse Fourier transform. Inverse Fourier transform. Okay, the existence of Fourier transform, that is called the, any function cannot be transformed. They must have follow the condition that is called the Dirichlet condition. Okay, so what are the Dirichlet condition? That is the first one is the function must be a single valued function. Means at a particular time the value of that function is fixed, not varying. That is called the single valued function. And the function has a finite number of discontinuities in every finite time interval. If function have discontinuities, if it is not required that the function must be discontinuous, no. If it have discontinuity, then the number of discontinuity that must be finite over finite interval of time. Further, each of these discontinuities must have be finite, the value finite. And third one, the function ft has a finite number of maxima and minima if it is there. That must be finite number in every finite time interval. And the function is absolutely integratable over the time interval minus infinity to infinity. Okay, means that the function, the integration of that particular function can be done with this period minus infinite to infinite. So that becomes a function that should be transformed into the Fourier expression. Here the some properties of the Fourier transform using that expression that we have already discussed. Based on that, we are having linearity property. If xt having Fourier transform value x omega and yt having Fourier transform value y omega, then the linearity property states that their addition and if they are multiplied by some constant, okay, then it is as it is here, it is axt plus byt, that is equal to ax omega plus by omega. If we are having some time shifting, if we are shifting time by some constant value, here it is the t is shifted by t naught, then x omega is multiplied by e की power minus j omega t naught. You can use that expression to find that. Okay, here it is x t plus t naught, it becomes, here it is positive e plus j omega t naught. Frequency domain, if you are xt having Fourier transform x omega, then frequency shifting property states that e की power j omega t into xt, that becomes x omega minus omega naught. Time reversal property is there. If xt is having Fourier transform, that is x omega, then if we are having the time reverse, then x of minus t that have a Fourier transform of x minus omega. Okay, here it is the time scaling property. If xt having the Fourier transform x omega, then if we are multiplying the time with some scalar quantity, or we divide the time with some scalar quantity, like x at, a is the scalar quantity, then it becomes x at, that becomes 1 of mod a x omega upon a. Here mod a means it does not depend on the sign of the a, but here it is as it is. If here let's take example is minus 2t, then it becomes 1 upon 2 x minus omega upon 2. Is it clear? Okay. Here it is the sixth one, differentiation in time domain power, that is important. If xt having the Fourier transform x omega, then how we transform that particular function if their derivative is there. So here it is dxt upon dt, that is j omega x omega. Okay, and if we are having a multiple derivation of that particular function, then we use dn xt dtn having Fourier transform, that is j omega to the power n into x omega. Okay, let n equal to 2, then it becomes d2 xt dt square, that is j omega square x omega, and what is the value of j square, that is minus 1 x omega. Okay, and the differentiation in frequency domain, if xt having Fourier transform x omega, then differentiation in frequency domain property states that if we multiply that particular function by t, then it becomes j dx omega upon d omega. Okay, integration property is also there. Xt, if xt having Fourier transform x omega, then integration property states that the first integration of that particular function that have a Fourier transform, that is 1 upon j omega x omega. Okay, but if we integrate multiple times, then it becomes 1 upon j omega to the power n. Here let's take, if you are having integration 2 times, then the Fourier transform, it becomes 1 upon j omega square x omega, and it becomes 1 upon j square means minus 1 upon omega square x omega. That is quite similar with the differentiation properties. Multiplication properties, if xt having x omega Fourier transform and yt having y omega Fourier transform, then their multiplication property states that xt into yt that have a Fourier transform x omega convolution y omega. Here it is the convolution property. If xt having x omega, yt having y omega, then the convolution of xt and yt is equal to 1 upon 2 pi x omega into y omega. Okay, let's have some discussion with the convolution xt convolution yt. So it is 0 to t x t minus tau y tau d tau. That is the convolution property. Here it is the duality, that is symmetry property. If xt having x omega, then duality property states that xt Fourier transform, that is 2 pi x minus omega. Fourier transform of important signal. First we discuss about the del t. Del t, that is the impulse function, unit impulse function. It is called unit impulse function. Okay, the value of del t, that is, it is equal to 1 for t equal to 0. The graph of xt is this one. At t equal to 0, the value of del t, that is 1, and at the value of del t becomes 0 at the rest of the value. Okay, so here when we defining it x omega minus infinity to infinity xt e की power minus j omega t dt, the value of xt that becomes 1 into del t, 1 e की power minus j omega t, and the property states that if we are having like this function ft dt, then it becomes f0, because del t, we can write del t, that is del t minus 0. Using this property, it becomes the function at the rate t equal to 0, e power minus j omega t, at t equal to 0, it becomes 1. So the Fourier transform of impulse function, that becomes 1. Okay, here we can see the magnitude spectrum and phase spectrum of x omega. What is the value of x omega? That becomes 1 and angle 0. So here it is the magnitude spectrum of this particular Fourier transform, and here it is the phase spectrum, means it having angle 0. So angle, that is 0. Similarly, f of del t minus t naught, using the time shifting property, we can have the Fourier transform of e power minus j omega t t naught. Single sided real exponential function e power minus at ut. Ut, first we define ut. What is ut? That is unit step function. It is unit step function 1 0. So ut having value 1 at the rate t is equal or greater than 0, and it having value 0 at all negative time. So you can draw it like this one. This one. Okay. So it means that the waveform of e power minus at at all positive time. Okay. Okay. So the value of exponential function xt, and by formula we are using it, and we found that the Fourier transform of xt becomes 1 upon a plus j omega. Okay. So these are the graphs of the magnitude spectrum, these are the phase spectrum. Okay. Okay, Jai Hind.